Hi, so in this video, we were talking about the motivation and historical perspective of deep learning. So if you have to describe deep learning in place of other discipline in AI, you can use this Venn diagram. So deep learning is a part of representation learning, which in part is a type of machine learning. And machine learning is one of the many ways to solve some AI problems. So this is how deep learning positioned itself in the field of AI. Now, deep learning is different from other representation and machine learning methods. So here's a structure that can help you understand why deep learning is different. So initially, a long time ago, machine learning is just a collection of hand-designed program that can take input and produce output. This is called rule-based system. Now, classic machine learning take an extra step. Basically, the mapping of the features, so you can learn the way of the feature to map from the hand-designed feature into the output. Now, we're taking the step further with representation learning to instead of hand-designed features, now we try to learn the feature itself, so it's added an extra block here. And finally, deep learning really looking at a composition of layers so you can build additional layer, more abstract layer up on simple features and so on and so forth and learn the mapping through a deep layers of or the networks of layers to go from the input to the output. So you can see that over time we keep adding more abstract or representation on top of the others. So representations really matter here because performance in traditional machine learnings depend heavily on the representation of the data. And for many tasks, it is difficult to extract such high level abstract feature from raw data. And typically, this process had to be done by human, and it require a sophisticated human level of understanding of the data. And representation learning trying to solve this problem. So an example, a classical example for this would be if you represent some data point in a Cartesian coordinate, sometimes you run into this problem where the data are not separable by a linear model. So it doesn't matter what line you fit here, you cannot separate the data. But if you look at it slightly different, you represent the data in a polar coordinate, perhaps. So all of these data points will map from the Cartesian to polar coordinate. And now in the polar coordinate, instead of x and y, now is theta and r, and it's all easily separated with the radius here. So you can see, depend on how you represent the data, it might have different transformation or representation that can be easily solved with much easier method. So that gives rise to deep learning, because deep learning by definition is an approach of AI that compute abstract representation in terms of other simpler representation. And typically these representations are built up in a multiple nested level, or you can call it a hierarchy. And so an example of that representation is shown here. So for example, if you look at a 2D image here, what you see is the input would be consist of just pixel from the image. And from there, instead of building high engineer heavy crafted features, these are just simple different layer of representation of these input pixels. And if you gonna compute a computational graph showing how these representations are built on top of each other, in this case, maybe the first we call it hidden layers here, because this is actually hidden from the data. These are not shown in the data, only the raw pixel input come from the data. And these are all computed based on that. So these are hidden away from the data. So multiple hidden layers here can compute different things, different type of features from the data. For example, the first feature maybe compute the edge in the image. The second hidden layer may compute or recognize corner and contour. The third layer might sum up with the object parts and so on and so forth until you end up with the object identity, right? So if you draw this computational graph, typically you will see that is built on top of each other, and the graph is typically deep with many layers. And this is the reason why deep learning, it explained the deep in deep learning. It wasn't about like a deep thinking or deep understanding, but rather is a deep in terms of the graph, computational graph. So let me show you an example of deep learning on classifying different numbers. So here we go. And this really nice application kind of show you different layers here. So if you draw any input, for example, if I draw some input, now it's certainly you can see here in representation of multiple layers in the network, and you can see each of these rely on the layer below. So for example, this is the input layer, and on some higher level here, you can see that it based on the value pixel on the lower layer and so on and so forth. Each of the layer build a even more abstract representation of the layer below, and so on and so forth until you reduce it down to the object categories. And so this approach seems to work very well. And I can show you a few more examples here. It's really tiny if you don't see, but there is a category 4 here it highlighted at the top of the representation. So you can see the mapping from raw input pixel all the way to the object categories. So that is essentially how deep learning on neural networks works. So what about a neural perspective of this deep learning, right? Why we call it artificial neural networks? Because in early model, it was a engineering system inspired by the brain or the biological network. But I use the word inspire here, but that's at much at the relation between artificial neural network and the brain. Typically in machine learning, the artificial neural network are not designed to be realistic models of the biological brain function. And now that is the field of neural scientific analysis, and that's separate from what we're trying to learn here. So the modern term of deep learning is not necessarily neuro-inspired, but it more appeal to the principle of learning at multiple level of representation. But because of historical reason, we typically prefer it at the artificial neural networks. So not only deep learning rely on our knowledge of the brain architecture, but draw heavily on the statistics and the applied mathematics. So we're going to talking about the historical timeline of deep learning. And even though deep learning appeared to be a very emerging field, it actually exists for a long, long time under many different names. And the branding and the naming really depend on the perspective of the research community at the time. But broadly speaking, there had been 3 waves of interest in deep learning. The first wave was known as cybernetics, and this is back in the 40s to the 60s. Second wave, deep learning would rebrand it as connectionism, and it's from the 80s and the 90s. And the third wave comes in, rebranded as deep learning, current state deep learning, from 2006 to present. And there is a quick collection of the frequency of the word speaking in a collection of books on Google Books. And if you look at all the frequencies here, you can see the cybernetics were really popular, a peak at the 70 and then dying off afterward, and then give it to the second wave for connectionism and neural network. Now the third waves are not shown here because it's too recent of the data, but you can see until now, you can see 2 separate waves that's shown here, depend on more words of the branding of deep learning we use. I'm sure if you're collecting more data recently, you can see another wave with the word deep learning. So talking about the first wave from the 40s and 60s. So it's all started in 1943 with McCulloch and Pitts. Inspired by the brain architecture, they have developed neurons and the theory of biological learning process. And that's sort of start a simplest model of a neuron. And then the perceptrons are created by Rosenbach in 1958 that could learn the weight that define the categories given the input from the training example. And then shortly after that, adaptive linear element or Adaline by Woodrow and Hoff that could predict numeric value from the data. And this is the first successful model of this type of neural network. And some of the early success lead to failed belief on these capabilities. And there's some backlash against this biological inspired learning led by Marvin Minsky and Seymour Papert from MIT, which is very prominent researcher at the time. And their main criticism is that these early model of deep learning, linear model, and so it couldn't learn some nonlinear distribution such as the XOR function. And that lead to a what known as the first winter of AI, where many of the promises go unfulfilled in the 70s. So it take about a decade for the second wave of deep learning to come back, and this time it's rebrand itself as connexionism. And this is throughout the 80s and the 90s. So in 1986, there is a revival in research interest in neural network led by the backpropagation algorithm by Roman Hart. And that led to the development of a few really interesting architectures for neural net. In 1994, there's advanced in modeling sequence using recurrent neural networks led by Joshua Bengio. In 1998, the early convolutional neural net by Ian LeCun, which result in LeNet-5, performed very well on the MNIST dataset of handwritten digits. And the result of this work is that the United States Post Office actually used this algorithm to detect zip codes and addresses. However, many researchers believe that generally deep networks are very difficult to train, and this belief lead to the second AI winter where neural net was not preferred over other methods like the kernel method with SVM and graphical model because they have outperformed neural net in some of the benchmark data sets. So they was used by other AI researchers. In 2014, this is the crucial point during the AI winter that the Canadian Institute of Advanced Research, or CIFAR, keep the research aligned with the Neural Computation and Adaptive Perception, or NCAP, research initiative, and led by the three main researcher, Hinton from University of Toronto, Bengio, University of Montreal, and Ian LeCun from New York University. And this particular group of researchers had keep the deep learning keep going through the second AI winter. And come the third wave, which is from 2000 and 2006 until present, and it rebrand at deep learning. And these all start in 2006 with a research breakthrough by Geoff Hinton, what called the deep belief network, that he figured out a way to train this network efficiently, use a strategy called greedy layer-wide pre-training. And that same strategy had been adapted by other researchers in the CIFAR group to all kind of neural net. And in 2012, the first deep learning method winning the ImageNet competition, which is the annual competition and sort of a very exciting competition at the time where all the learning method trying to classify over the ImageNet dataset, which is one of the main benchmarking dataset for image classification. So AlexNet, which is from the Hinton group, was the first deep learning method that won the competition. And from there is a flourish in development and research in deep learning with the development of generative adversarial network in 2014, and also expansion in deep reinforcement learning with the excitement of AlphaGo and AlphaZero, where it can beat the world champion in a game of Go, and also playing all kind of Atari games and beat the human level. So until the present days, the deep learning has seen tremendous growth in popularity and also at its usefulness. But the questions remain: will this new wave of interest last, or are we gonna approach another AI winter? So for this time, we have reason to believe that it maybe will have impact, and the reason is there are four main reasons about the data, the hardware, the algorithms, and the investment. So let's look at each of these reasons in slightly more details. So reason number one is about data. The game changer of deep learning had been the rise of the internet and the age of big data, which make feasible to collect huge amount of data, training example for machine learning. So you can see user-generated tag on Flickr images or YouTube videos. The ImageNet dataset and its annual competition provide great way for people to collecting data, and also Wikipedia have been used for the natural language processing. And the graph below here show you how data grow over time. So that if you look at timeline, the data set grow in the 10th of powers, and you can see the MNIST data set is in 10th of thousand, the ImageNet data set reaching millions, and we are actually approaching up to billion with the WMT, which is a transition from French to English data set. So the data now is widely available, helping machine learning, deep learning algorithm to flourish. Reason number two is hardware, and this is in accordance with Moore's law. We now have a lot more computational resource to run much larger model today compared to previously. So from 1990 to 2010, the CPU performance had grown by 5,000 times. And even better, there is an advent of GPUs for parallel computing, and neural networks can contain of many small matrix multiplications, so which greatly benefit from highly parallelizable system. And this even go beyond the graphical processing unit GPU, because recently Google reviewed its Tensor processing unit, which is a new chip designed from the ground up to run deep learning neural networks, which is promised to be over 10 times faster than even GPU. And we also benefit from network connectivity with fast internet and I/O. So these trends are expected to be well into the futures. So this is the number three, is about algorithmic improvement. And previously, part of the second winter of AI is that the backpropagation of deep neural net have sort of could manage or the signal or the feedback signal get faded away with the deep stack of layers. And since then, there is many algorithmic improvement that allow better gradient propagation. So things better activation, weight initializations, more advanced optimization scheme, and also various algorithmic innovations that we will actually cover in the upcoming videos that help pushing the deep learning framework forward. Also, it's worth noting that there is more effort put on the software infrastructure and libraries. Now, many open source libraries available for deep learning. And so we're gonna look at these software library, in particular TensorFlow, to implement our method as well. But then with this appearance of open source library, it's so much easier for practitioner of deep learning to use and utilize neural net. So reason number four is about the investment. And since deep learning had become state of the art for computer vision and eventually all perceptual tasks, the leader from the industry start taking note and paying more attention to deep learning. And so the amount of money going to the venture capital investment in AI, or particularly more deep learning startups, go from 90 million in 2011 to a staggering 384 million in 2014. Many tech giants also invested heavily on their R&D departments. So Google acquired DeepMind, which is a deep learning startup, for $500 million in 2013. Baidu started a deep learning research center in Silicon Valley, and Intel bought the deep learning hardware Nevada system in 2016. So research progress had reached a frenetic pace, with many researchers now want to go into do research in deep learning in the academic as well as industry. So all of these reasons give us hope that deep learning will be here to stay. And perhaps the pinnacle of this timeline is when ACM announced the 2018 Turing Awards, which often refer at the Nobel Prize of Deep Learning, a $1 million prize, was given to the original research group for the CIFAR initiative, which is Joshua Bengio, Geoffrey Hinton, and Jan LeCun. And so they was given this Turing Awards for making deep learning a critical component of computing. And through this story, I just want to say this is just an inspiration story of perseverance and determination. Go through a up and down of deep learning when it not popular and when no much attention paid to it. These researchers believe in their approach and keep going through the AI winters. And so we're going to learn more about their approach. We're going to learn more about them in upcoming videos. And I'm very excited to share those with you. Right? I'll see you in the next video.